Swayam Prabha. Digital India. Educated India.
Good morning, friends. Once again I welcome you to this course, and today last lecture I have covered slope stability analysis, some introductory methods, and first one was infinite slope and second one different type of slopes of with C5 soil, and based on assumption of a particular slip surface, and methods are already explained, and I will take a problem now to explain or illustrate how to use this method. So, the problem was this is the problem, the embankment in the figure made up of soil with phi equal to 20 degrees and C equal to 20 kilonewton per meter square, and soil on which the embankment sits has a phi of 7 degrees and C equal to 75 kilonewton per meter square, and for this for both soils unit weight is 19.3 kilonewton per meter cube, and determine the factor of safety for the slip circle shown. That means next figure I will just show these are the things. This is the slope basically from started from here to started from here to here. This is the slope surface, and this is the sloping surface, and this is the level surface, and this is the one level ground, and this is the original ground level. Suppose this is embankment is made. For the embankment soil, C is 20 and phi is also 20 degrees and C also 20 kPa, and this slope angle is 35 degrees, and this embankment was built over a soil that having C equal to 75 kilo kPa and phi is 7 degrees. Now, to find out the factor of safety, as I have explained before, that you need to assume a slip surface, different slip surface, and finally you have to find out where your factor of safety become critical, and that will be the actual slip surface. So, here on that suppose we assume that on that process we have reached or assumed one slip surface which is started from here and become tangential and reached here, and this is one, and another slip surface we assume suppose started from here and it gone below deep and then reached here. So, this is one slip and this is another slip. So, if you have this is the slip surface, what is the factor of safety you have to find out? If this is the slip surface, what is the factor of safety you have to find out. So, these two actually while solving the problem or to find out the factor of safety for a particular slope, we assume different slips. So, two such slips taken as example, and I am showing the calculation procedure to how to find out finally the value of value of factor of safety. So, next slide. So, this is the one. Suppose first I will the embankment resting on a steep layer, and the slip circle tangential to the lower layer will give a lower factor of safety. So, that we will finally will show you that. So, we are assuming the first one it is given like that, and we have already explained that when this type of problem we solve, and typically we need to divide into number of slices. So, here suppose the angle was 76 degrees, and then this portion of the circular arc, and it is surrounded by this slope line and this level line, and we approximately divide into 4 different parts, part 1, part 2, part 3 and part 4. Now, in these actually we need to if you put in a graph sheet, and in a particular scale, and then if I finally if I in the graph sheet, if I do by counting the number of blocks, approximately you can find out the area of this, similar area of this, area of this, area of this. And if I find out the area of this particular portion of the slope, and then if I multiply by the unit width, suppose the slope is perpendicular to this 1 meter, then if I multiply by 1, then you will get the volume, and then unit weight of soil you multiply, then you will get the soil weight. So, soil weight will act vertically. So, that you have to show with a particular scale, and then you have to draw tangent and normal to this point to get the reaction and tangential force. So, for each slice. So, that is the one graphically can be done. So, first calculate the weight of each and draw a vertical line, and then from there in scale you draw a normal from here, and from here you draw tangential to this. So, then you will get the this is T component and this is N component, this is N component, these are all N, and these are actually T, this T, T, this is T, like that. So, if I do in the graph paper, then this easily can be done. So, I will show this table form, the calculation of this in the tabular form. Suppose the first one, sorry. So, for this I will suppose take a new sheet, slice number, and then area, suppose in meter square, then weight, and then normal component, and that is N, and tangential component, that is T, that is in factor safety equation N and T is there. So, slice number 1, 2, 3, 4, slice number 1 area become 3.7 meter square, and this become 8.7, and it is 11.6, and this is 2.7, and then if I multiply by simply the unit weight, will get the weight, because its unit length is taken. So, this becomes 71, 19 into 3.7, 19.3 into 3.7, this become 168, this become 224, this become 148. And now, graphically, when I get a bottom of the slice, suppose something like this, and I get weight here, then I will draw a tangent and then this. So, this become your T, this become your N. So, from there graphically I can draw that, and then I will get this is 71 itself, because it is a very minor difference will come. This is 163, this is 191, and this one 104, and whereas this one will come -7, and this one will be 42, this one is coming 116, and this one is coming 106. Now, sigma n equal to 529 and sigma t equal to 257. Now, your sigma n tan phi will be equal to 529 multiplied by 0.364 equal to 193, and C r theta, that will be equal to C is 20 multiplied by r is 10.7 is given, multiplied by 76 degrees was the angle, divided by 180 into multiplied by pi to convert into radian. So, this gives you total 284 kilonewton. So, your factor of safety equation will be equal to C r theta plus sigma tan phi divided by sigma t. This is the expression. So, if I now put all the values, that is 192 plus 284 divided by 257. So, that gives you factor of safety equal to 1.85. So, this problem is done without taking any your tension crack. So, as I have told, I have discussed before that there is a C5 soil, there can be a tension crack, and depth of tension crack we can find out. HC expression, HC depth of tension crack will be 2C into gamma root Ka, and here your Ka 1 minus sin phi by 1 plus sin phi, if I do, it gives you the value 0.49. So, if I put all those values here, this comes 2.96 meter, and so that means if I take from the right side, so I can go back. So, this is the one. Now, if I take a tension crack here, if I take tension crack here, this tension crack depth actually have got now 2.96, and that means beyond that actually this portion will not consider any shearing resistance. So, you have now your slip surface become this length, but entire weight has to be considered. So, this angle become now 58 degrees, and if the angle become 58 degrees, then your C r theta become 20 multiplied by 10.7 multiplied by 58 divided by 180 multiplied by pi. So, that gives you only 217. So, C r theta is reduced actually, and other things are unchanged. So, your factor of safety will become 192 plus 217 divided by 257. So, that factor of safety 1.59. So, that means, if I consider a factor of your slip surface was your slope was something like this, and if I consider a tension crack here, now without tension crack your factor of safety was 1.85, and with tension crack factor of safety is 1.59. So, it is reduced. Obviously, why it is reduced? Because I am considering entire disturbing force same, but while calculating the resistance I am not considering this one, and that is required because when the C soil contains possesses C value, there is a chance of tension crack, and tension crack depth theoretically we know 2 C by gamma root Ka. So, from there actually if I take the remaining length for resistance calculation, then I can get the modified value of resistance, and from there I can find out the value of factor of safety. So, this is the one first case, and second case if I consider now, which is passing through the second layer also. So, you can see now the second one, this is the one, and in this you can see now the initially we are not taking tension crack. So, I am taking from here to here, and this angle was total angle was 85 plus 45, and then your C for this portion is 20. So, it is divided into two parts, because resistance is passing from this to this, that is one part, and resistance from here to here, though total angle is 85 plus 45, then 120 and 130, but I have to divide two parts, because while calculating resistance this portion I will use C value as 20, While calculating within this zone, I will use C value equal to 75. The procedure is similar. So, again I can divide into number of slices 1, 2, 3, 4, 5 slices, and each slice actually again I can find out the area multiplied by the unit weight will give you the weight, and from there actually I can draw a vertical line that gives you vertical force which is in scale, and then I can draw a normal and I can draw a tangent to intersect this point. Then I will get the normal value, I will get the value tangential value. Similarly, for this also I get the weight, this is the weight, and then normal here and tangential here, then again weight, this is the weight, and this is the normal and this is the tangential tangent. So, the T and N we can get. So, like that for all cases like previously you have done, we can find out, and you can see direction of T, these two was reverse. So, this will be minus and this will be all plus. So, now we will see the tabulation how to do this one. So, tabulation if we do similarly, slice number, then area, then weight, then normal component, and then tangential component. So, slice number 1, 2, 3, 4, 5, and this is area was 3.7, this was 9.7, this is 16.6, this one on 19.2, this was 14.3, and this is 71. This was, if I multiply with 19.3, then this is 187, this is 320, this is 370, and this will come 276. Now, the graphically if I draw normal and tangent from the vertical, then I will get normal component for this one is 61, 184, this 316, this one 322, and this one 162, and for this tangential component this will be minus 36, this is minus 33, this is 52, this is 186, and this is 224. So, sigma T will be equal to 393, and sigma n, I will for two different layer, I will do sigma n for upper layer, sigma n for upper layer will be equal to 162, and sigma n for lower layer will be equal to 883. So, now sigma n tan phi. So, sigma n tan phi, that is one component, and since it is passed through two layers. So, I will do 162 multiplied by 0.364, that tan 20 degrees, plus 883 multiplied by tan 7 degrees, that is directly I can write 0.123. This is tan 7 degrees and this is tan 20 degrees, because first layer has first layer is having phi equal to 20 degrees, second layer is 7 degrees. So, if you do this value comes 169, and C r theta if I do, that is again 75 the value multiplied by 9.1 is radius multiplied by 85, because first layer 85 degrees by 180 multiplied by pi plus 20 multiplied by radius is 9.15 multiplied the angle is 45 divided by 180 multiplied by pi. So, this all calculation if I do, that comes 1163. So, your f equal to C r theta. So, this C r theta plus sigma n tan phi divided by n sigma n. So, if I do that, or sigma t then this will be equal to this is sigma t. So, this will become 1163 plus 168 divided by 393, and that gives you a factor of safety equal to 3.39. So, that means if I take the second one, which is the slip surface passing through the second layer actually, then it will get more longer resistance zone, and of course, this is actually one can visualize that when the slip surface is longer, more will be the resistance, and factor of safety will be larger. So, that is what we have initially commented, and you can see for this case we have got a very large value of factor of safety. That means, probability of having slip will be tangential to the, when there is a two layer actually, it is generally the it is supposed to be, or it is expected to be tangential to the bottom layer. So, this problem again can be modified, because there can be a tension crack. We can also theoretically can find out what is the value of tension crack, that 2 c by gamma, and from there we can subtract the length of slip surface, and then recalculate the resistance, and then use this formula again, and you can find out, considering tension crack, considering tension crack, same problem can be done if S equal to come there 2.95. Okay. So, these are the two problems, same problem only we have solved for assuming two different slip surface. Now, I will continue to the next thing. So, this is one method of calculating factor of safety, and for this is actually basically graphical procedure. You have to do lot of graphical work, and finally, after doing so many assumed slip surface, you will get the critical factor of safety, and then corresponding to critical factor of safety you will be the actual slip surface. That is one way can be done. There are actually many methods in the literature, and then another popular method, actually rapid method, by using stability chart. Actually, it is given by Taylor, and it can be seen. So, the rapid determination of F for a homogeneous regular slope. So, if it is irregular and non-homogeneous, obviously you will not be able to do. It can be shown that for two similar slopes made up of two different soils, the ratio Cm by gamma h, Cm means cohesion mobilized, actually it is Cm by gamma h. This ratio is same for each slope, provided that the two soils have the same range of friction, same angle of friction, angle of friction. The ratio of Cm gamma is known as the stability number, and is given the symbol n. So, it is n, where the Cm is the cohesion mobilized in regard total stress, gamma is the unit weight of the soil, and h is the vertical height. So, if the slope is something like this, if the slope height is h, and if the C mobilized and your unit weight is gamma, then you can express that non-dimensional form, that is n stability number, and with respect to this stability number of charts are provided, and using those chart one can find out the factor of safety quite quickly. So, those factor of safeties are the chart, those charts are something like this. One chart is given, Taylor prepared two curves that relate the stability number to the angle of slope. The first is for the general case of a C phi soil, while the second is the phi equal to 0, and you can see this is the chart given, and either you can do two ways. Generally your phi of the soil is required, it generally will be known, and if it is known and phi and C, then you have to what is the slope angle you can provide. So, from here actually if I know the C value and unit weight and height, then I can calculate this quantity. Sorry, I can calculate this quantity. So, suppose this quantity is fixed, suppose some value I got 0.1, and then if I know the phi value, suppose phi value is phi value is suppose 20 degrees. So, phi value is 20 degrees suppose, then our expected angle of slope. This is of course not so straightforward. I will explain how to use this one. If it is then expected from here, actually you can find out the angle of slope from here. So, that is one way of using the chart. So, if I know, or otherwise if you know the angle, then I can find out knowing the friction angle, and these two combination I can find out also what is the n required, and once n is required is known. So, h is known and gamma is known, then what is the C required for the soil, that also can be obtained. So, this is different ways this problem can be solved. That means, your either soil, generally your soil parameter will be known, and once you know the soil parameter, what could be the shape angle of slope. And here actually when we are doing this, we calculating a value of n and then projecting to that on the particular line corresponding to phi of soil, and then from there whatever angle we are getting there, actually we are assuming the factor of safety as 1, but actually factor of safety will not be 1. So, if when there is a factor of safety is different than 1, then actually you have to assume factor of safety for a particular phi, and then based on that you reduce the value of phi and then find out the angle, and then from that angle you find out the C value, and then whatever value of C you are getting and whatever the C value is available, then find out the factor of safety. And since the two soil parameter we cannot apply two different factor of safety, the factor of safety should be same. So, whatever assumption you made initially for the factor of safety of phi, and finally after using this chart based on stability number, whatever factor of safety you are getting for cohesion, they should be equal. If they are not equal, that means your assumption was not correct. Then what you have to do? You have to modify your assumption, that means change the factor of safety what you assumed for phi, and then again reduce the value of phi and then find out the value of C, and based on that C value find out again factor of safety for C. When they are converging slowly, if you change, modify the value of the factor of safety, then you will see sometime it will converge, and both assumed factor of safety and the final factor of safety for C both are merging or becoming close, and when they are becoming equal, then that is the actual factor of safety for the slope. So, that is the way actually stability chart can be used. So, this is one stability chart as given. There is one more was there for slightly different one, that is actually this is also when slope is different this type of this type, then there is another chart. So, both can be utilized for finding out the factor of safety, or if I know all those details, factor of safety everything, then what will be the corresponding shape slope angle, that also can be determined. So, these are the two charts given by Taylors and can be utilized for quickly determining the value of factor of safety. So, with this I will just close here and I will do the next section rest of the things. Thank you.